right, so today,
Hey, Lindsay.
everybody say hi to Lindsay.
Hi,
Lindsay. Yo, Lindsay is hard.
Lindsay.
All right.
Let's throw Lindsay a rap. I can't. I'm not going to do it anymore.
Nathan had a 6-3 style, Lindsay.
And you missed it.
Yeah, it was like the sickest freestyle I've ever heard.
And you missed it. I dedicate it to you.
He didn't actually say that, but
Spiritually.
Okay. All right, so now we need to look at diffraction patterns. Now, what is, first of all, let me remind you, what is the definition of diffraction?
Bending of light. Oh, the
It is not rewrite.
movement of light through different mediums.
No, that's,
Causing. No, that's refraction.
I got it.
Diffraction is
Oh,
the bending of waves around objects in it.
that's rewrite.
Excellent. Bending of a wave around a barrier. So, so if I have a wave coming around here, right, then what you might expect to see, if you don't understand diffraction, is that the bottom half of the wave gets cut off and carries over like that. But what you see in reality is, because of Huygens' principle, which Huygens' principle just says that any part of a wave can be seen as the propagation of a new wave. Right here, this part of the wave, by Huygens' principle, creates a new wave. And so, instead, I see that. In other words, this wave bent around that barrier. And that's diffraction. And you'll recall from last year, possibly, that this explains why if I hold my hand up in front of a light source, like if I did in front of the projector here, you would see my hand.
Are you recording the screen?
Yeah.
That's unfortunate.
So, but the shadow of my hand, right, and let me go over and see this, but
Yeah.
the shadow of my hand is
Shadow of your...
Bigger than your head. Bigger than.
what do you notice?
It's like lighter on the side.
What's the difference between that shadow?
Really? And go that one's
Yeah.
blurry.
This one's blurry, right? The fuzzy shadow. The reason it's fuzzy here, more so than here,
Because the light would come back around.
good, because the light bends around my hand before it hits the screen there. And that's the difference between what we call the umbra and the penumbra. Right? The umbra is the dark part under the shadow, and the penumbra is that fuzzy edge. Okay? That's caused by diffraction.
Do we need to know
I mean, it's not on the exam, but to be an educated physics student, it's good to know.
what umbra and what?
Umbra
Bruh.
and penumbra.
Let's write it down. Bruh. Umbrella, what'd you say? Umbrella.
Umbra is the dark.
Umbra is the darkest part in here. And then the fuzzy part on the edge that's caused by the diffraction of the light around my hand before it hits the screen is the penumbra. All right, so then if I have a barrier like this, then exactly, you got this.
Wow.
Right, it does that because, again, by Huygens' principle, the wave front here propagates a new wave that then spreads out. So little tiny holes, which what characteristic did you learn last year, or what phenomenon did you learn last year that is explained by this? Good. Why the sky's blue? The sky is blue because of the oxygen and nitrogen molecules in the atmosphere acting as little tiny barriers, holes like this, that the light then diffracts through. And remember the... Now,
Refraction is like you see like a wet spot on the street. Oh yeah.
yes, it's a mirage, but it's also why there's a few extra minutes of sun at sunset.
Yeah, but what like the frequency small like shorter and like blue.
Right. Well, yes, but it's also, they diffract more easily too. And so they spread out first. That's why the sunset is orange, right? Because it goes through more of the atmosphere, and so we get those longer wavelengths. All right. Now, there was. All right. Now, I'm going to send a light wave through this tiny opening. Now, if I do that, then some light will go straight. And over here we're going to have a screen. Okay. So let's now. So the red ray goes straight through. But there's also another path from the opening to that part of the screen that we're labeled with this blue ray. Now, the first question I would ask myself, actually, I'm sorry, let me back up.
These are just not like actual colors.
No. All right. I'm sorry, let me... Here's what I meant to say, sorry. Sunlight goes from this edge to a point on the screen here, the red path. I mean, what I said before was true, but that's not what we're interested in. What we're interested in is the difference between that and this. Another ray of light goes from this edge to the same point. All right? Right. Now, what that means is, if I zoom in here, and I draw a normal line, a perpendicular line here, what I'm interested in is how much farther, right here, this distance right here, how much farther did the red light travel than the blue light? And again, it's not red and blue light. The light represented by the red ray and the light represented by the blue ray. We've got just like a laser. It's a single wavelength of light. The red line traveled farther, that amount right there. Now the question is, what is that amount? If this if this over here is some distance x, where here is a minimum, what's happening at that point? We'll call that point P.
I have no idea.
It's a dark spot,
A dark spot?
a dark area.
Here.
They're canceling each other out, right? They're destructively interfering. Right?
When it's always
Yes.
always the minimum, does that mean it's always destructive or not?
Yes. Always destructive, cause minimum. Yes.
I don't understand how the deadline's longer if you draw the, I get that it's longer, but if you draw along the position of that section, like, could it be like a triangle and the blue line would be like a button, so you can
Okay. Yeah, the blue line might be longer than this section of the red line, but the red line includes this part that sticks out here. Okay? Now, so if point P is a minimum, it's where there's destructive interference. It's a dark line. Then that means the distance traveled by the red ray is, as I just pointed out, a half wavelength farther. Right? Because if you shift it a half wavelength, then it cancels out. Now, in the interest of time, and by the way, let me toss this up here. I'll try and remember to add a link to Net Classroom. But whether I do or not, if you just do a search for hyperphysics concepts, there's a university site that has a concept map that is excellent for, I'm not going to derive some equations right now. If you want to go back and pick that up and see how to derive it, this is a great resource. Plus, just from here on out, a lot of times things are going to feel rushed with what we're doing nuclear and everything, because we're going to start moving towards the review portion. And so you spend a lot less time in class doing deriving the formulas for you. So if you're interested, this website does a really good job of that. Soon. Like, we're getting close. We've got like probably 3 or 4 more classes where I'm going to actually present new material. Yeah. Okay. Yes.
I can do it at my house, yeah, not this weekend, but I'll do next weekend.
Okay. That weekend's actually bad for me because my mom will be in town.
I can't.
Oh wait, no, the 8th and 9th. That weekend works for me. Yes, we can see. We can look at that. Okay, now. If I okay, this is where it gets a little sticky, so pay attention. If I zoom in on this area right here, then I've got the path difference line, and I've got the normal line, and I've got this guy, and we're going to dot this just so it looks different than the solid path difference. And then we've got the normal, or the line straight from the opening to the screen. and this is labeled as the angle theta. Now, this
I know you wanted
this right here is what we call little d. Remember, d is most often used as a distance, as a separation distance, and that's the case here. It's the width of this slit, this little tiny opening that we're shooting the light through. Now, the path distance then is related to d by this. For very large values for L, which is the distance between the screen and the slit, and very small values of D. In other words, if L is much bigger than D, then we can do some small angle approximations. And I can say that this distance is equal to d sine theta, because this angle is very similar to this angle, and for very small angles, tan and sine become the same. Right? Again, if you want to see it in slow motion, I can do it for you later, or you can go to that website. But just know that small angle approximations allow us to say that this angle is the same as that angle, and therefore this is equal to d times, this is equal to d times sine of theta. Right? So, yes. And the red line is the path difference. So d sine theta is the path difference. Well, then over here, there are integers that I can multiply by the wavelength to explain the diffraction pattern over here. And whether they are whole integers or half integers depends on the type of interference I have. It's just an integer. It's I said half integers, right? That's kind of funny. But it can be half of them as well. But right now, just 1, 2, 3, 4. Because there's a thanks for that. Because there's another point up here, right, where this happens again. And this time, the path difference is greater. It's twice as much. And that's the M. That's that energy. All right? No. M is just an integer. There's going to be a first order minimum. There's going to be a second order minimum. There's going to be a third order minimum. The integers are 1, 2, and 3. And each time the difference increases. Right. Right. Now, again, using small angle approximations, because this is true, I can say that this value of x then is related to this as, well, and we usually use approximately equal to because of the small angle approximation. M lambda of L over D, right? Did I do that right? If that's x over L, that's equal. Yeah, that's right.
X is approximate to,
Right.
And X is the blue line, right?
No, X is how far away from the center point this minimum occurs, this P. Now, so that's kind of the background, the derivation. What's the point? What's the application? Well, the good news is pretty much easy points, because this is what you're going to see. You're going to see a question like this. It's going to say, a single slit diffraction, or single slit has a laser that's producing a monochromatic light source of 700 nanometers. And by the way, you're going to do a lab on this too. And the student, the screen is 6 meters away. And the student observes that there's a bright spot in the center, right, which you would expect. But then they also observe that a distance of 0.7 centimeters away, there's a minimum. And the question then would be, what is the width of the slit? Now, I shouldn't have done this, by the way. I should have done this. Okay. Because, honestly, the only way you're going to miss these problems is, number one, forget the difference between single and double, which we're going to get to in just a second. Or number two, forget what letter corresponds to what reality. It's the only way you're going to lose points on something like this. Or, sorry, third way is if you forget that it applies to all waves at all times. So, those three ways are the only ways you're going to lose points on these kinds of problems. No, this is definitely a free response. I mean, they could have a question on free response, on multiple choice related to this, but they're few and far between. Okay? So, what do I need? Yeah, X equals M wavelength L over D, and I'm solving for D. Is that another wavelength? Yeah. So this is who? Big L. This is who? X. And I'm looking for little d. Again, those three distance variables, if you keep them straight, you're in pretty good shape. Actually, there's 4 distance variables, aren't there? The only thing that's not a distance variable is m. That's why it's confusing. But if you get them straight, keep them straight, it becomes easy. So now all we need to know is m. What is m? It's 1. How do I know it's 1? It's the very first minimum. It's what we call the first order. Because I said that there was a bright spot, and then right next to it there was a dim spot. Then, well, it wouldn't be a fair question if they didn't tell me about it. I mean, they probably would say the very first, the very next, or whatever. But yeah.
Okay, say it was like the third one that spot away. How many did that?
Yeah, if it's the third minimum, then what is M? 3.
Okay, I didn't know.
Now, be careful though. Huh? Yeah. Yeah, you got to express everything in meters. But also be careful about this. If they give me this distance here, alright, I know it went ridiculously high. Sorry, not 4.1 meters. Let's keep it at least somewhat reasonable speed. 2.12. Okay, that was that. Do I divide that by 3? Yeah, it depends, right, on what if I'm going to use M equal to 3 or 1. So I can just talk about the distance between the maxima, the minima, and the difference in the orders is 1. It's only when I'm talking about the distance that covers multiple minima that I have to worry about the integral. All right?
So you could just divide by that and not worry about making it?
Yeah. Yeah. Because they're going to be evenly spaced because of the symmetry of the problem. All right? Okay, next time we'll